So do you guys usually start at?
And I'm going to introduce Ankur. It is my pleasure to introduce Ankur Moitra. He is the Nobel winner professor of mathematics at MIT, and he's the director of the Statistics and Data Science Center. And he has won uncountable awards. And it's my pleasure to have you here to give a talk. So yeah, thank you.
Thanks for the kind introduction. So I'm Ankur Moitra. I'll be talking about algorithmic foundations for the diffraction limit. And this is based on joint work with my former PhD student, Sitan Chen. So, what this talk will be about is about revisiting some basic inverse problems, specifically in optics, from the perspective of theoretical machine learning, and trying to understand what are the right ways to pose the problems there and to think about fundamental limits. So I'll assume, like me, you know very little about optics. So let me tell you the little bit that I know, which is about the physics of diffraction, which is really the starting point for thinking about what the diffraction limit means. So you can think about what's a cartoon model for, the perfect idealized physical setup, for optics. And you can imagine that you have a perfectly spherical lens with a circular aperture, and you're observing some kind of far away point sources like stars through this circular aperture. And what you get is you observe an image in this observational plane. And the pattern that you see, I'll get into it in the next slide, but it's really governed by the physics of how Fraunhofer diffraction limit works. And so what's important is that, in this perfect physical setup where you're observing a faraway point source like a star, well, what you're getting is you're getting readings of photons being recorded on this observation plane. And you can think about the normalized intensity function that just represents the probability density function of, what's the chance of observing a photon in any position in this 2D plane. And this intensity pattern is called an airy disk. So the notion of an airy disk goes back a long time, over 150 years. So let me tell you what it is mathematically. So the airy disk is, this function. You can see it drawn on the right, where, the white parts are the parts where the intensity is the largest. In the middle, it looks a little bit like a Gaussian, but then it has some oscillation, which you can see with these faint rings. So mathematically, it comes from, Bessel functions of the first kind. And one of the important parameters of this airy disk is this parameter sigma that represents the blur. So the important thing is that this is governed by physical properties of your optic setup, things like the numerical aperture of your lens, and it governs how spread out this point source becomes when you observe it in this kind of setup. And as I mentioned, the airy disk is really interpreted as something that you get from measuring. It's the infinitesimal probability of detecting a photon at some position in the observation plane. So these functions are named after Sir George Biddell Airy, who in 1835 explicitly computed what this intensity function would look like using Fraunhofer diffraction. And now I can start getting into things like, what do we mean by diffraction limit once we have this notion of the airy disk in hand? So the basic idea about the diffraction limit is that, for more than a century and a half, really since Airy's work, it's been widely believed, with an emphasis on believed, that physics imposes some fundamental limits to resolution. And really it comes down to something like the following picture, that if you're observing two faraway stars through your lens, and remember that the physical properties of your lens govern the blur, well, then that should tell you whether or not you can tell if it's one star or two stars. Because the closer these two objects get, the more and more they look like a single airy disk instead of a pair. Now, the arguments weren't really rigorous, and I'll go through a little bit of some of the historical debates about what exactly is the diffraction limit and what does it mean. But my main motivation in this talk is trying to understand whether we can put this on a rigorous foundation. So are there statistical and maybe even algorithmic limitations to how accurately we can estimate a mixture of airy disks and actually decide with some given physical setup, whether it's 1 or 2 stars. So let's talk about fundamental statistical limits as our way of thinking about how physics really does impose some diffraction limit. So let me summarize it with this picture, but I'll get into some more of the details about some of the debates surrounding diffraction in a few minutes. But for a long time, people have tried to address this question about what should the minimum separation be between the centers of these two airy disks, and how should that depend on the parameters of your physical setup of this optical system so that it's possible to resolve whether it's a single airy disk or a pair of airy disks, and even better, to learn the locations of their centers. So in fact, there's a long line of work on this spanning over a century. And if you remember, sigma is this blur parameter. Pi also shows up in the natural way to measure the pairwise separation, which you're thinking of as just being the Euclidean distance in 2D between the different centers of the airy disks. And there are a lot of criteria that people have suggested over the years at what exactly the pairwise separation should be. There's a criteria due to Abbe, there's a very famous one due to Rayleigh, Schuster, Dawes, Houston, Buxton, all of the luminaries of physics from the 1800s, even Sparrow's work in the early 1900s. And one of the questions I want to ask is, which, if any of these criteria, is the right one? For reasons that I'll get into, these criteria were really derived through heuristic reasons, but maybe there's a way to statistically vet what is the right criteria to begin with. So we had a lot of fun in this project, digging into some of the history after we realized that we had a nice mathematical and algorithmic question to solve, because you can really go back to some of these original papers. Now, sometimes they're not written in English, but there are a lot of English translations of these papers because they're important. And you can see what some of the luminaries of the time said about what is diffraction and what is the diffraction limit. So when Rayleigh in 1879 proposed his famous criteria, he very much recognized the fact that it's a heuristic, because what he was saying was that this rule is convenient just because it's simple. And maybe there's not a precise way to make sense of what resolution means in the first place. Now, over time, people got a little bit more bold when they proposed new diffraction limit and resolution criteria. In fact, a lot of times when I teach undergrad discrete math, where we learn a lot about the basics of how to prove elementary statements. And on the first day, we have this overview about top 10 warning signs or pitfalls of doing proof-based math. And one of the things that we always tell them is proof by intimidation. How could you not understand this proof? Of course it's correct. Well, with that, let me introduce you to Carroll Sparrow, who introduced a new resolution criteria. And let me just read in his own words what he said in 1918. So he not only introduced the criteria, but he took it as patently obvious that it was the right criteria to begin with. It's obvious that the undulation condition should set an upper limit to the resolving power. We also talk about, a proof by appealing to authority, and he does both of them here. My own observations on this point have been checked by a number of friends and colleagues. Clearly, everyone can see that this is the right and universal notion of what the diffraction limit is. A lot of these things, they are very intuitive. What, Sparrow's criteria really boil down to is that when you take these two airy disks and you move them closer and closer together, at some point they become unimodal in the middle, and something different happens with the way that they oscillate. And that's how he derived his numerical value for it. And there are others who pushed back on the idea that there really is a diffraction limit at all. Maybe it's not just that it's difficult to make sense of it, or it's obvious if you look at it the right way, but maybe the question doesn't even make sense unless you're very careful in how you pose it. So this goes back to, for example, Feynman's famous introductory physics lectures, where he says, it seems a little pedantic to put such precision into the resolving power formula. And what he says is, actually, if you get sufficiently careful measurements, if you take a lot of measurements of photons and you record their locations very precisely, and you get this exact intensity distribution, then maybe you can resolve regardless of the Rayleigh criteria or anything else. Maybe you can always push beneath whatever you think is the diffraction limit. Now, I'll give it a little bit of foreshadowing. Feynman is basically right on this, but it's really a more subtle question because a natural way to think about what the diffraction limit will emerge, not when you're looking at mixtures of two airy disks, but when you're looking at mixtures of many airy disks. And then there really is a way to make sense of this question using the language of statistical phase transitions. I also want to mention that, this isn't just a, academic debate, but there's also decades of empirical evidence from different communities that care about resolution in astronomy or in microscopy. And they all seem to have different criteria that they favor and different rules of thumb about what they believe about diffraction. So can we put the diffraction limit on a rigorous foundation by thinking about it as a statistical inverse problem? So let me tell you about some of our main results, and then I'll interpret them, and then I'll roll up my sleeves and tell you some of the main technical ideas that draw on a lot of ideas from modern analytic number theory actually to prove sharp bounds. But our first main result is that we give the first provable algorithms for learning mixtures of airy disks that have non-asymptotic guarantees. So what I mean by that is if you want to learn the parameters of a linear combination of two airy disks, and you give me some upper bound epsilon on the precision that you want to learn their centers to within an additive epsilon, well, then what you really care about are non-asymptotic guarantees. How should my number of samples, the number of photons I have to observe, scale with epsilon? How should the running time of my algorithm depend on epsilon too? So prior to our work, the only things that were known were things in the limit as epsilon goes to infinity. So they don't actually give quantitative bounds on resolution. So the first thing that we proved is that, that Feynman is right. There is no real diffraction limit, at least if you're talking about just a mixture of two airy disks. So in that case, if you think about k being equal to 2, so it's a constant, then what I claim is that if you're given samples from a mixture of two airy disks where the centers are delta separated for some parameter delta, and by delta separated, I mean they're delta far, the two centers, in Euclidean distance, and suppose that the relative intensity is at least lambda, meaning that the mixing weight that you have some chance of a typical photon from the sample of coming from at least one of the two different the airy disks in your mixture. What you can give is you can give a polytime algorithm that learns up to accuracy epsilon for any epsilon and up to some failure probability delta. And the running time and sample complexity depend polynomially on 1 over this target accuracy epsilon. So at least in all of these hypothetical thought experiments where you're talking about just a mixture of two airy disks, there is no hard and fast diffraction limit. Any line in the sand you draw, when I'm given more samples and more running time, I can rigorously resolve beneath that threshold. So that's the first main result. And, as I was saying, many of the arguments, the heuristic arguments about the existence of a diffraction limit, they stem from reasoning about just mixtures of two airy disks. And what I'm claiming is that there really is no fundamental statistical limit to what can be resolved in this setting. Now, I also want to comment a little bit on, the sample complexity here. What I'm saying is that the number of photons that you observe, this is supposed to scale as poly in 1 over epsilon. A lot of times from an experimental standpoint, what this means is that this is your exposure time. So how long you're collecting photons in some optics experiment. But it can also manifest in other ways, because even when you record a photon, you don't record its location perfectly. So there is a way to translate back and forth between, other notions, physical limitations to your setup, like if you only record the locations of a photon within some additive accuracy gamma, then you can think about it as only being able to estimate this intensity function up to some small additive error. And what we're saying is, as long as you can drive this additive error to be polynomially small in your target accuracy, you can rigorously resolve mixtures of two airy disks. Now, at the same time, something very surprising happens, which, on the one hand, when there's only two airy disks, there isn't a real diffraction limit. But on the other hand, actually, when you think about the number of centers becoming large, then there's a very interesting statistical phase transition that emerges that can help you pin down and say that there really is a diffraction limit. So let me tell you two constants that show up in our upper and lower bounds. They have to do, the upper bound side, gamma plus, has to do with some zeros of Bessel functions, but it works out numerically to about the value 1.53. On the lower bound side, we have a parameter gamma minus that has to do with an explicit construction that we give, which has to do with triangular lattices. And the way that that works out numerically is about 1.15. And what I claim is that if the mixture of airy disks is gamma plus times this pi sigma separated, then there's a polytime algorithm, not just for constant k, but an algorithm that runs in polytime even when k is large. So it's polynomial in k as well. And it learns up to accuracy epsilon, again, with some failure probability delta. Now, the really interesting thing to go along with this, not only when you are above some critical separation, do you improve the running time and sample complexity to polynomial in k, but conversely, if you're not well separated, if you're at least gamma minus times pi sigma close for these mixtures of k airy disks, then you can explicitly construct an example that requires exponential in k many samples to learn, even from an information theoretic standpoint. And as I mentioned, with any reasonable physical setup in optics with finite exposure time, finite precision in recording locations of photons, what these lower bounds mean is that there really is a fundamental limit to resolving many point sources that are below some critical spacing. And there's a question in the chat, which is this all about the two-dimensional setting? Yes. And I'll tell you a little bit more also about the one-dimensional setting and the higher dimensional setting later, because there are a lot of interesting extra results we can prove in the 1D case. And there are a lot of interesting open questions in the higher dimensional case, but great question. Please feel free to add into the Q&A any chat questions you might have. So what I want to do first, before I roll up my sleeves and tell you a bit more about the technical ingredients that go into this, let me get a little bit more philosophical, which is, to this day, there are a lot of debates about the diffraction limit. On the one hand, there are domains like astronomy, where you're trying to resolve stars. And they really talk about this double star problem of trying to figure out whether it's one or two stars that have very small angular separation. And in these types of domains, you don't really expect many close by sources. Maybe there's at most one or two or three stars, in a clump. And in those types of domains, it's taken, as common knowledge that there really shouldn't be a diffraction limit. And there are all kinds of heuristics that people deploy that seem to go beneath the diffraction limit. Well, in those cases, really super resolution is possible in a rigorous sense. But at the same time, simultaneously, in other domains like microscopy, where you're trying to look inside a cell and see what's going on, there are a lot of very closely spaced particles, and super resolution, ought to be impossible, at least without tampering with the system by doing things like tagging the particles with photolipids like they do in super resolution cameras. So this is sort of borne out empirically because there are successful heuristics in astronomy. And in microscopy, it's long believed that there is a diffraction limit, and you need these fundamentally new experimental techniques, things like super resolution cameras that let you do amazing things, like see how the HIV virus enters a cell using new experimental techniques that even won the Nobel Prize in chemistry pretty recently. So there's a question in the chat, which is, what is the role of wavelengths? Usually you need short wavelengths to resolve short distances. So that's a great question. I think I'm going to answer that best when I get into the technical parts of the talk, because many of the abstractions people had tried for understanding the diffraction limit, they explicitly have some notion of how your object is, your sensing device is only able to measure what you care about with low frequencies. because then at high frequencies, you might be imparting so much energy that you might destroy the thing you're measuring, like the cell. Now, in this case, in the setup that I'm talking about, the one that goes back to Airy, it's a little bit harder to figure out where the frequency bound comes in, but it really comes in through the properties of the Airy disk, and the sigma parameter that governs the blur is where it's going to show up. So later in my talk, when I talk about what are the actual algorithms for doing it, I'll show you where band limiting the types of measurements you have naturally shows up when you talk about the inverse problem for learning mixtures of Airy disks. So ask me again then if I still haven't answered your question. Okay, and let me tell you one last really cool thing, which is, I was belaboring this statistical phase transition, which I think is really neat, but there's a cool way that you can put a spin on it, which is you can visualize what the diffraction limit means as a statistical inverse problem. So first, I claim that in 1D, we don't have upper and lower bounds that are off by some constant factors. We can fully pinpoint what the diffraction limit is, and it's the Abbe limit, which is the limit where the leading constant is 1. So I want to point out that in 1D, the diffraction limit is different than what our lower bound is in 2D. So these problems really are fundamentally different. But in 1D, where we know exactly what the diffraction limit is, you can think about doing something like varying the number of centers in your mixture of Airy disks and asking statistically how many samples you need in order to distinguish and even tell how many centers there are in the mixture to begin with. And what happens is, around some critical threshold, which is this parameter 0 right here, because that corresponds to the Abbe limit, what happens is that these curves that represent the natural log of the TV distance, or 1 over the sample complexity for solving the hypothesis testing problem, they bend away from each other. Because once you're beneath this diffraction limit, then all of a sudden increasing K makes the problem much, much more statistically hard in a way that above the Abbe limit, it has a limited effect. So this is a neat way where you can actually visualize statistically what the diffraction limit means as a phase transition. And it almost looks like light going through a prism and bending and separating right around this Abbe diffraction limit. And there's a question in the chat, which is, what would be special for the Airy density? Can we derive the same theoretical results for more general classes of probability densities? 100% yes. Now, the Airy disk, I think, is the most well-posed way to study this because it really does correspond to a perfect physical setup. But the arguments that I'm going to give you when I get into the technical ideas, I'll explain how they're not really that specific to Airy disks at all. In fact, at the very end of the talk, I'll talk about what got me interested in this question to begin with. Is in my neck of the woods, I spent a lot of time thinking about statistical inverse problems like learning mixtures of Gaussians. And what really got me interested in this work was thinking about how the language we've developed in statistical learning theory and theoretical machine learning for learning mixture models might give us a better sense of how to pose inverse problems in physics and understand statistical limits. So I'll say more about that, but honestly, it's a much more general phenomenon for sure. Okay, so I've kind of run out of time for talking about the philosophy, and now all that's left to do is to prove some interesting things. Now, some parts of this I'll give you more and less intuition for, but the first thing that I want to do is tell you about a very natural algorithmic technique for trying to learn a mixture of Airy disks. And what I'm telling you about here isn't all that specific to Airy disks. It's a general strategy you can try for low dimensional mixture models, but it's based on the idea of deconvolution. And then I'll tell you about how that changes our problem, and it actually has some pretty striking connections to modern analytic number theory. So there's a very natural strategy for trying to deconvolve by an Airy disk, by trying to remove this convolution of an Airy disk is, through the Fourier transform and division. So let me go through this slowly. So let's think about our diffracted image. We have K different centers. They happen at these different, values mu j. And just to make sure we're on the same page, these are 2D vectors, the mu j's, because they represent the coordinates of the center of each Airy disk within our observation plane. Now, we also have these relative intensities lambda j that just represent the mixing weights. If I take a random photon that I'm observing in my optics experiment, what's the chance that it comes from the jth component, the jth star that I'm observing? That's lambda j, that's the relative intensity. And what I get is this overall mixture model, rho of x. I'm getting samples from it. Now we can think about this as convolution in the obvious way, because I can think about it as having a bunch of Dirac delta functions at each one of these locations mu j, where I put a mixing weight lambda j on it, but my diffracted image is now the convolution of these sum of delta functions with the airy disk. So what I really want to do is I want to remove this convolution. I want to do deconvolution. There's another, there's a comment in the chat. Yes, another term for convolution is deblur. So these things are used interchangeably. Now, let's make our problem a bit simpler. Let's take the Fourier transform of the diffracted image. I'll talk about this later, but if I'm given enough samples for my diffracted image, I can create a good approximation to it. And then when I take the Fourier transform of that, that'll be a good approximation to the true Fourier transform. So what is the true Fourier transform? Well, shifting the centers of these airy disks by this parameter mu j instead corresponds to multiplying by a trigonometric polynomial, right? And this trigonometric polynomial looks like e to the minus 2 pi I. And I take the inner product now between this two-dimensional vector mu j and the corresponding two-dimensional frequency omega. But of course, I change my airy disk to the Fourier transform of the airy disk. Now, the airy disk, I didn't really explain too much. I said it has something to do with Bessel functions. But here's the right way to think about what the airy disk is. I think it's easier to think about it in terms of the Fourier transform. So if you take in the Fourier domain the solid disk, and you convolve the solid disk in 2D with itself, that is the Fourier transform of the airy disk. That's the thing that you derive through Fraunhofer diffraction, is it has to do with how the circular aperture interferes with itself in terms of how the physics of light works. But what this tells us is that this Fourier transform of the airy disk, it has a very simple property, which is, what does the zero non-zero pattern of the solid disk convolved with itself look like? Well, it's non-zero on some disk around zero, and outside that disk, it's going to be zero. So what I claim, and you can see it from this expression, is that I hat of omega, the Fourier transform of the airy disk, is non-zero exactly on the disk of radius 1 over pi sigma centered at 0. Now, this makes sense, right? Because, as sigma gets, larger and larger, which means that the object has more and more blur in terms of our physical setup, then the Fourier transform of this airy disk is acting more and more like it's band limiting our observations, because we're pointwise multiplying by I hat of omega, and it's killing all but a much smaller set of the frequencies. So the question we can ask is, can we remove this I hat of omega term, at least in the region where it's non-zero? In the region where it's 0, there's nothing I can do. I get no information. So now it's a very simple trick, as what we can do is I claim is we can pretend and reduce our problem down to the problem of recovering the parameters of an exponential sum. I claim what you can do is you can just divide by I hat omega, because you know what it is. And what you can do is, given your samples from this optic setup, you can simulate noisy access to the exponential sum f of omega, which is written down here, but only for omegas which are in this disk of radius 1 over pi sigma. So, just to be precise, the way that you would do this is you would draw a bunch of samples from the true density function rho of x that corresponds to measurements of photons. Now, that will be an empirical estimate. So it's not smooth, and it's not a good approximation to rho of x, at least in L1 norm. But you can do the standard statistical trick, which is you form a kernel density estimate, meaning that you take your empirical density and you just smooth it by convolving with a very small variance Gaussian. And because we have some smoothness bounds on rho of X, and because we take enough samples, that kernel density estimate really will be a good estimate of rho of X in the L1 norm. And then when you take both of their Fourier transforms, they'll be good approximations to each other in the L infinity norm. And then you can pointwise divide by I hat of omega. And that proves the lemma right here, that for our problem, we can pretend that we have noisy access to this exponential sum. So now we're getting something that looks a lot more like a familiar statistical inverse problem. These types of noisy access to exponential sums show up in a lot of theoretical machine learning problems. And the basic question is, can we estimate the centers from being able to query f of omega within this disk? So let me tell you a little bit about, how to digest this problem. Now, this problem is a little bit different than the way that we usually study it because it's happening in 2D, right? So f of omega is a function on 2D because I can plug in any omega that's a 2D vector in the disk. One of the simplest strategies we could try is we could try to only query f of omega on a line in frequency space. Now, this approach is going to have some issues and it'll work for some parts of the problem. But the way to think about it is that if we're taking the way that we can query f of omega and we're restricting it in the Fourier domain, well, in the original spatial domain, this corresponds to a projection. So it's like taking your original linear combination of airy disks, which might look like this, and you're really projecting it onto a 1D line. This has some problems because it means that you might decrease the separation because they might be more separated in 2D than what you get when you project onto 1D. So this approach might make resolution harder, but let's try it as a first cut. Okay, so in fact, if we take this 1D line in the frequency space, what we can do is we can imagine sampling f of omega and measuring it at least some sort of arithmetic progression. So we start off querying it at some value a in the disk, and then we query it at the point a plus b, and then a plus 2b, and so on. And what I claim is that our vector of measurements looks like the following linear algebraic setup. What's really going on is that there's some unknown Vandermonde matrix, and we're multiplying it by a vector of coefficients, the C1 through CK. So in particular, these alpha j's that we're raising to different powers, they look like e to the minus 2 pi I, mu j, inner product with b, and then we have some coefficients. Because this makes sense, because what we're plugging in for omega is a and a plus b and a plus 2b and so on. And remember that in our exponential sum f of omega, we're taking the inner product between omega and these mu j centers. So this is exactly what the functional form looks like if we try the strategy of querying f of omega along an evenly spaced sequence of points along a single line. Okay, so in fact, what can we say about algorithms for actually recovering what these alpha j's and the mu j's are just from querying these exponential sums? So I won't get into it in this talk, but I'll just assert that this algorithm exists. There's an algorithm that you might have heard of called the matrix pencil method, and it's based on solving a generalized eigenvalue problem. And the basic setting is that it works without noise. So a standard fact about the matrix pencil method, which says something interesting about our setting, is that it's possible to recover the sum of k exponentials exactly like we get access to, provided that you have access to 2k plus 1 noiseless measurements. The trouble is that in our setup, noise is unavoidable because it comes from things like the fact that I don't observe the actual diffraction pattern perfectly. I don't see the intensity profile perfectly. Instead, I only get samples, which represent photons. So I get an imperfect measurement of the diffraction pattern. What can you say about the matrix pencil method when it's working with noise? Actually, it turns out that the algorithm and its guarantees are much more subtle. This is something that I worked on, a fair number of years ago. which is one of the things that I showed was that the matrix pencil method, well, whether or not it works in the presence of noise, that depends on the condition number of that Vandermonde matrix that showed up. So in the case where you have noiseless measurements, the condition number of the Vandermonde matrix is irrelevant. You just need that it has full column rank. And that happens as long as all of the centers μj are disjoint. But once you care about things like what is the smallest singular value and is it exponentially small, then the problems become much more subtle because it has to do with what are the separation conditions. So the first main fact that we proved, about the super resolution setup, about learning these linear combinations of airy disks, was that we showed that, if you take some delta separated point sources in 2D and you randomly project on a 1D line, well, the separation doesn't go down too much. It might go down to something like delta over K. And then as long as you take these evenly spaced measurements, what you can do is you can lower bound the smallest singular value of the corresponding Vandermonde matrix. And that's exactly what gives us the first main algorithm for resolving any linear combination of two airy disks, is because while the Vandermonde matrix might be exponentially ill-conditioned, it's only exponential in K ill-conditioned. So then you can combine this deconvolution approach with the matrix pencil method with lower bounds on the smallest singular value and get a provable algorithm for learning linear combinations of K airy disks. And in fact, what you can do is that really only resolves what the 1D projections look like on that single line. But it turns out that when you project on a second line, there's a way to pair up the estimates so that you really figure out which points correspond to the same center, and you piece together what are their two-dimensional centers. Now, the most interesting part that I want to tell you about is let's dig a little bit deeper, right? I think at the end of the day, it's not that surprising that you can learn any linear combination of two airy disks, regardless of what their separation is. But I think the much more interesting aspect is that there's a phase transition as a function of K. And, let's think about this corresponding smallest singular value of the Vandermonde matrix, because really that's the thing that ought to govern whether we can actually solve the inverse problem of learning a mixture of airy disks or not. So it turns out, this was the main result in my paper a number of years ago, was that if you think about those Vandermonde matrices, where you're taking powers of these alpha j's that look like e to the minus 2 pi I, inner product of mu j with b raised to different powers, well, then it turns out that the smallest singular value of the Vandermonde matrix undergoes a phase transition, that it really has to do with what the cutoff frequency is. Say when you're querying this exponential sum along a line in some direction, remember that you're limited to only querying it along a disk. And the diameter of that disk is what tells you, how much you can vary the frequencies by which you can measure it. Now, there turns out to be a way to show that the cutoff frequency is related to the smallest separation that you can resolve. So what I showed back in 2015 was that if the cutoff frequency, in our case, that's the diameter of that disk, which is 1 over pi sigma, is at least 1 over the min separation, then you can lower bound the smallest singular value, and it's not exponentially small in K, it's larger than that. But conversely, if the separation is smaller than this critical threshold of 1 over delta, then the smallest singular value undergoes a phase transition and becomes exponentially small in K. So the approach that I had was actually based on some connections to analytic number theory. So the idea was based on this beautiful function from analytic number theory, which is called the Berling-Selberg majorant. It was the first time I learned about it. I encourage you to, take a look. It's a pretty amazing thing. And I'll tell you at a high level what happens with this Berling-Selberg majorant. And then I'll tell you about, the new analysis that comes up in trying to solve higher dimensional versions of these types of problems. Well, you can take something like the sine function, SGN, which is a function from minus infinity to plus infinity that just outputs, -1 when you're on the left of the y-axis and +1 on the right side of the x-axis. So that's the function in black that I've denoted here. It's just the step function. Now this function is not very smooth, right? And has a discrete jump. So if you take its Fourier transform, it definitely doesn't have bounded frequencies. One of the questions that people studied in analytic number theory was, what's the best smooth approximator to the sine function? So what they did was they asked, well, if I restrict you to functions whose Fourier transform is supported in the interval -1 to 1, so they have bounded frequencies, and you always want that function to be above the sine function, above this black curve, what's the closest that you can get them? And the answer to that question is exactly the Berling-Selberg majorant. It's kind of amazing that, there is a function whose Fourier transform is supported in the interval -1, 1, where this red function, where it always majorizes, it's always above the black curve. But if you look at the integral of their L1 distance, then you get the value 1, even though it's an integral from -infinity to +infinity. And correspondingly, there's a lower bound, which is just what you get from flipping the picture. That's the blue curve, and it's usually called a minorant. So these things are very useful as test functions in analytic number theory. But it turns out what they also give you is they give you a way to design explicit preconditioners for the van der Maan matrix so that you can multiply them by the right diagonal matrices that have to do with the Fourier transforms of the Berling-Selberg majorants that show that not only is the smallest singular value lower bounded, but you can precondition it so that it's a well-conditioned matrix you're multiplying by. So that turns out to be the key to proving that these inverse problems can be solved. And what I want to do now is, with this in hand, I want to think about the 2D problem, which we really care about. So the same way that in 1D, you can in some cases, under a separation limit, under a separation criteria, you can improve the dependence on K from exponential to not even showing up at all. You can ask whether the same thing can be done in 2D. So in 2D, when all of the centers are separated from each other, is there some critical separation condition at which I can get not just an algorithm for learning mixtures of K airy disks, but one whose dependence on K is polynomial? Now, there's a big catch to this, which is very easy to see geometrically, which is this whole approach we had of taking a 2D problem and projecting it onto 1D doesn't work. If you think about having a bunch of centers which look like this, so they're all connected to each other, so they come in pairs, but you slowly rotate them around the circle as you go from left to right. These are, centers which are separated in 2D, because for any pair of centers, they're far apart in Euclidean distance. The trouble is that any 1D projection you choose is going to cause one of the pair of centers to almost collide. So that, stinks, because it means that it's not just a failure of the technique. The trouble is that really in 2D, the answer for what is the right limit for diffraction is bounded away from the Abbe limit, because it was this funny parameter 1.15 that I told you about. So we need totally different techniques that need to attack the problem natively in 2D. So kind of amazingly, I told you that much of this talk is really intertwined with recent progress in analytic number theory. So even though these Berling-Selberg majorants are classic topics that have been known since the 40s and 50s, the understanding of what's the right high-dimensional analog of the Berling-Selberg majorant has really only been figured out recently. So there's a result just from a couple of years ago of Goncalves, where what he showed was the following. He constructed explicit functions that are going to sound a lot like the high-dimensional analog of what the Berling-Selberg majorant is. So first of all, what you want is that that the function that you're looking for, m of x, these high-dimensional extremal functions, they minorize the indicator function of the unit ball. So if you look at the ball 0, 1 in 2D, you can just look at the indicator function, which is really just the solid disk. And you want your function m of x to always be less than or equal to that indicator function. It could go negative, that's fine. The other thing that you want is you want that the function m hat has bounded Fourier transforms so that it should be smooth. That way the indicator function alone doesn't work. So you want that the support of m hat is itself contained within the ball of radius r, right? And so these two conditions alone would be trivial to satisfy because, I could just take the zero function. But, now what I want is I want it to be good. So in fact, what you can do is you can ask that m hat of 0 is strictly positive. And what this means is that it's a non-trivial approximation to the indicator function of the unit ball, because m hat of 0 measures its total L1 mass. So in fact, in the case of 1D, the answer to this sort of extremal question is exactly the Berling-Selberg majorants. But amazingly, we know exactly how to construct these things in higher dimensions. It has to do with something called the study of de Brange spaces, which I don't really know much about. If you know something about it, email me and try and teach me. That would be awesome. But we can use them as a part of our algorithms, the same way that we use the Berling-Selberg majorant. We can use them as a type of preconditioner to make this problem of learning from this exponential sum and disentangling its parameters well posed so that it works in the presence of noise. So it turns out that there's a tensor decomposition approach of Huang and Kakade that looks a little bit like the matrix pencil method, but instead of reducing to a 1D problem, it works in higher dimensions. So what they do is they try a bunch of measurements. These are the omega i's, and they form some giant matrix that represents, what are the inner products of, the different centers with those frequency measurements. And you keep track of them through some exponential sums. And it turns out that, these new extremal functions in 2 and higher D that we now know exist and can construct, what they do is they give you a way to bound the condition number of this matrix and to show that you really can solve this inverse problem of learning the parameters of an exponential sum under these separation conditions in 2D. So, putting this all together, what this means is if we go back to our original picture, where we had all of these guesses and heuristics about where the diffraction limit is, well, if we study it as a rigorous statistical inverse problem, the question about at what critical separation can I learn the centers of a mixture of airy disks within a polynomial number of samples, then we know that there's a sharp phase transition where the problem goes from poly in K to exponential in K. And we've pinned down where exactly that phase transition happens to within some interval. The upper bounds come from these de Brange spaces and these constructions of extremal functions. The lower bounds come from some explicit lower bounds and constructions that we have. But we can actually do things like rule out some of the other conjectured diffraction limits, some of the stuff that goes back, for example, to Sparrow. And we can say that, the only 2 criteria that at least survive are the ones due to Raleigh and Buxton. It's a super interesting question to pin down exactly what the sharp phase transition is. Seems very intertwined with giving sharper answers to some very challenging questions in analysis, and harmonic analysis specifically. But, if you solve that, I'd be very excited. But what I want to do now is I want to take a step back and go back to the philosophy. So, before this talk, I really didn't, before I worked on this, I really didn't know much about optics. I certainly didn't know what Fraunhofer diffraction was, what airy disks were. But, one of the things that got me interested in this was, coming across things like the Nobel Prize laudation for super resolution cameras that won this Nobel Prize. Because in the laudation, they make a bunch of arguments about why there ought to be a diffraction limit. And a lot of those arguments were very heuristic in nature, but they sounded a lot like inverse problems that we study in my neck of the woods, problems like learning mixtures of Gaussians. These things go way back, to really the founding of modern statistics and the method of moments. For example, there's a very famous problem dating back to Carl Pearson, where he studied the problem of, in 1D, can you learn a mixture of two Gaussians? And he had this amazing data set where what he was doing was he was interested in biology, and he took some particular species of crab called the Naples crab, and he measured some physical characteristics of that crab, of each particular sample he had. In his case, it was something like the ratio of the forehead length of the crab to its circumference. And he plotted the frequency of occurrence of different values. And he was very shocked to find that, this green curve, this approximator that he had, it wasn't Gaussian. It wasn't even symmetric around its maximum value. And what he postulated was that maybe the Naples crab wasn't a single species of crab, but was really, two crabs. And he postulated that maybe there's a way to fit it as a mixture of two Gaussians. And he introduced the method of moments as a way to try and heuristically solve this problem. So this is something that I worked on, about 10, 15 years ago, where we gave rigorous algorithms for learning mixtures of Gaussians, even when the Gaussians are so close that they become unimodal for the overall mixture. Now that sounds a lot like those pictures that I showed you in the beginning, that even when you move the airy disks closer and closer to each other, and the diffraction pattern becomes unimodal in the middle, that doesn't mean that learning is impossible. The right way to think about what's possible or not is to try and prove rigorous statistical lower bounds, and conversely, to give algorithms on the other side. So, what I wonder is, in optics or in physics more generally, we can think of a lot of problems that we would like to estimate as being an inverse problem. Maybe there's a lot of gains to be had by thinking about them as a statistical inverse problem by leveraging things like the method of moments, statistical lower bounds based on parameter matching, to try and shed some new light on what is and isn't possible in different kinds of inverse problems that, we don't encounter as much in our neck of the woods. So what I really wonder is whether tools from theoretical machine learning, like the method of moments, and provable algorithms for learning mixture models, maybe there's a lot more that they can say that's exciting about inverse problems that show up in other walks of science. So I'll stop there because I'm basically out of time, but let me give you my high-level summary. Some parts were technical, some parts were philosophical, but the main thing that I wanted to get across was that the diffraction limit is a very interesting idea. It comes from some cartoon ideas of what's the world's simplest setup, physical setup for optics. And you can think about the diffraction limit as an inverse problem, where you're getting samples from photons. That lets you think about what are rigorous notions of statistical upper and lower bounds. Now, no such bounds were known, but what we did was based on connections to other learning algorithms for mixture models to deconvolution, we showed fundamental limits in optics, and we showed, most importantly, the emergence of the statistical phase transition beneath some critical threshold. And are there other inverse problems in the sciences that are amenable to tools in theoretical machine learning? So I'll stop there, and I think there are some questions in the chat, which I'll try and get to. But thanks for your attention. So there's a question in the chat, which I think I didn't answer yet, is how big is the typical condition number of the van der Waals matrix? So that's a great question. So, if you think about even in 1D, let me go back to just showing you what the van der Waals matrix looks like. So, our van der Waals matrix, our setup looked like this. We have complex values, the alpha j's, whose phase depends on the parameters we want to learn. And we're taking powers of these alpha j's, and that represents the columns in our van der Waals matrix. Now, a lot of times when you think about the van der Waals matrix, you need not be taking powers of something that is a complex value with unit norm. You could be taking powers of any value you want. And in those cases, the van der Waals matrix is usually exponentially ill-conditioned as a function of k. Because the way to think about it is that, solving a linear system in the van der Waals matrix, it's, not too hard to see that it represents things like, if I can evaluate the polynomial of a polynomial of degree d at d plus 1 points, can you solve for what the coefficients of that polynomial are? Now, in that case, the answer itself, you can find it by solving a linear system involving the Vandermonde matrix. But the trouble is that the answer is just exponentially ill-conditioned, because tiny changes in the noise, when you evaluate the polynomial at some point, but you add a tiny stochastic noise, that can exponentially blow up when you talk about how it affects the coefficients of the polynomial that you fit. Now, the amazing thing that a lot of this work is really based on is the idea that even though over the reals, the Vandermonde matrix is just never well-conditioned, over the complex numbers, it is well-conditioned in interesting cases. Because you can think about a very simple case where all of these alpha j's that I'm taking powers of are evenly spaced around the boundary of the unit disk in the complex plane. In that case, the square Vandermonde matrix is just the DFT matrix. So it's perfectly well-conditioned. And more generally, the things that I was doing about using the Berling-Selberg majorand to analyze the condition number of the Vandermonde matrix, it has to do with the interplay between, beyond just the DFT case, what's the minimum separation between the different points along the boundary of the complex disk, and how that's related to the number of rows in the Vandermonde matrix in terms of when it makes the problem well-conditioned or exponentially ill-conditioned. So that's exactly the phase transition, but it's a subtle problem that has to do with moving from the reals to the complex numbers, and it's connected to a lot of other things like interpolation for polynomials. So hopefully that answers your question. And there's a comment, it is a scalar theory only valid for objects much larger than the wavelength. Yeah, I don't know what that means, but sounds interesting. And I also don't know what inverse SAR is, but tell me more. So are there any other questions?
That's a question in the Q&A as well.
Okay, so there's a question in the Q&A. In microscopy, the diffraction limit can also be seen as the finite window multiplied on the Fourier transform of the object signal, which truncates the high spatial frequency and thus cannot resolve two close point sources. Definitely. Would it be possible to explain the mathematics of super resolution in this point of view? Namely, can the super resolution from the proof and algorithms in this presentation be explained in that view? Yes. So in fact, there's some work that goes back to, some of the early work on this was due to Carlos Fernandez Granda and Emmanuel Candes, where the basic idea was that they thought about, in 1 and 2D, exactly this kind of setup. What happens if you have an exponential sum? So imagine that you have point sources, which are like delta functions, and you're only allowed to take low frequency measurements. Now, when you take a low frequency measurement of these point sources, what you get is exactly the exponential sum that I got out after I deconvolved by the Airy disk. So these two things are very intimately related. Now, the subtlety there is that in Fernandez Granda and Candes's work, what they were doing was they were writing down convex programs that work well. But their first wave of analysis was really only in the noiseless setting. Now, the funny thing is, if you think about this in connection to the matrix pencil method, the matrix pencil method tells you that when you have no noise, then there is no limit. It doesn't matter what the separation is. Any 2k plus 1 measurements suffice to recover exactly and perfectly what those points are, even if you're restricted to low frequency measurements. So the thing that got me interested in it back in 2015 was exactly their work. Was I wanted to understand what happens when you introduce noise. That's exactly where the subtleties come in, because then, not only does the matrix pencil method break down when you add noise, because of properties like the phase transition in the singular values and the conditioning of the Vandermonde matrix, but the problem becomes statistically impossible beneath some separation condition. So in fact, the thing that got me interested in thinking about, Airy disks was after that work, I remember a colleague told me, boy, the super resolution cameras recently won the Nobel Prize in chemistry. Maybe you should mention them in your talks. And I started reading the laudation. And then I realized that the argument they were making about the laudation, really looked a lot like mixtures of Gaussians to me. They were saying something about how when two airy disks are too close to each other, you couldn't resolve them. And I thought, hey, we worked on that problem for mixtures of Gaussians, and that's not true. So let's try and refute this heuristic in the context of airy disks instead. So definitely these things are all related, and tons of other interesting open questions too. Great. Yeah, thanks for your attention. And any other questions, I'm happy to take them over email.
Okay. Thank you so much for an amazing talk. Yeah.
Thanks.
Yeah, it was great. Thanks a lot.